of the vector space generated by the powers of A. Space. Let me call this V. This is the span of these guys. Let me call this V. The space of the vector space V. This is exactly n. N plus 1. Let me say. No, this is a vector space of dimension n. So this is surprising that if you took matrices, if instead of taking powers, you were squaring the entries or powering the entries, then you would actually need n squared plus 1. A generic matrix, if you're powering the entries, has maximum span. But if you did matrix multiplication, the span is smaller. And if you write this as a system of linear equation, you get that the coefficients are going to be expressed in terms of the determinants. So if you did not know the determinant beforehand, and you wanted to recover it, just solving the linear equations coming from here would give you the Cayley-Hamilton theorem. So if
then how Cayley-Hamilton could have discovered it with mathematical
yes. I would argue this is correct. Now, what is convenient for us in combinatorics is that these actually have combinatorial interpretation. A to the k has something to do with the number of paths of length k that connects I and j, every entry. And we're saying there's a non-trivial dependence between them. All right. Now that we have all the combinatorial tools, what would we do for hypermatrices? So clearly, there is a way of combining powers of a hypermatrix. And how should we do it? And so we know how to multiply them. How should we do the powers? Now, matrix multiplication is associative. Unfortunately, hypermatrix multiplication is not associative. So when you talk about powers, since in mathematics we hate choice, you must fairly choose all of them. You must allow any subset of powers you want. And you should sample your powers from the so-called product tree. If you had A, you multiply it by itself. This is the only way you can compute powers with 3 elements. The product is ternary. You need 3 of them. All right. Here already things start getting messy. So you can put this guy. This is one way of doing it. You can put this guy in the middle. A, circle. A. And you can put it at the end. A. All right, and you continue. You continue. So you can notice that for every multiplication you do, the number of operands that has to appear has to be odd. You will never be in a situation where you have an even number of operands. The number of operands is always odd. Now you ask, if you were treating each one of these results as a vector, and you try to see how many you needed before you start getting non-trivial linear dependency, how many do you need? So those who believe the answer would be n, please raise your hand. Those who believe the answer should be n squared, please raise your hand.
Maybe it's depth, n.
All right. Those, so I have one vote for n?
No, depth.
I like
Depth
that.
n.
Not the n, but
All right, so
specific depth.
Ask the question. Start.
So the choices, there's three choices for this exam. There's n squared, or n cubed.
Okay.
Those who vote for n, raise your hand. Those who vote for n squared. This is n squared or n? N squared. This is n squared. Okay, great. Those who vote for n cubed, raise your hand. Nobody votes for n cubed? Just you? Okay, that's very nice. It turns out the answer is n cubed. Oh. You're not as lucky as for matrices. Alright, so it turns out the answer is n cubed. If you want linear dependency, so to convince yourself that n squared is no good, you can take small examples. It's easy to come up with hypermatrices 2 by 2 by 2.
Disappointing. It's n cubed.
Yes, it is disappointing. It is somewhat disappointing. Somehow counting these sequences.
It's much deeper than that.
So I don't know quite what it means. But depending on the assumption you make, you can show that it should be n cubed always. So here's the difficulty we have. In practice, we want to show that it's n cubed. Why do we want to show? Do we suspect is n cubed? Well, you try 2 by 2 by 2, you can exhibit a hypermatrix which requires n cubed to get linear dependence, no matter which subset of n cubed you pick. This is important. So you try any subset you want, generically there's one that's going to require you to get n cubed. For 3 by 3, we can't try all subsets. Well, we can try it. We can see that if you try at random any subset of them from the experiments we did, you need n cubed. For 4 by 4, we are able to show this as well. And 5 by 5 is very easy to see. Now, it could be that we're looking at some large constant times n squared. And it looks to us like n cubed. All right. So if you make the assumption that the mass dimension must be some fixed polynomial, which doesn't change, then it suffices to try 4 values. Because this is a polynomial of degree 3. If there's a fixed polynomial which is at most n cubed, and if it works for all the first 5 values, then it should be true always. However, this assumption that it should be a fixed polynomial is not natural. In other words, if you don't give me that assumption, I do not know how to prove experimentally that the polynomials you get by looking at here, are actually have to spend the maximum span. Right? So this is the open question. Relax the assumption that it should be a fixed polynomial. How do you show that if you do these composition of powers, any subset of n cubed is going to be linearly independent? I mean, n cubed minus 1 for some generic matrix. But when we say we want to formulate the Cayley-Hamilton, what do we mean? What we mean is the following. If you take n cubed of them, then you can use Cramer's rule to solve for the coefficients. And these coefficients describe a non-trivial dependency between the counts of the number of simplices that you build. The number of simplices that span a particular triangle. So you build a tetrahedral simplices by gluing tetrahedrons. And if you want to glue 2 tetrahedrons, how many could you do using the edges of your hypergraph? If you want to glue 3 tetrahedrons, how many could you do? We're saying there's a non-trivial dependency between them. We can use Cramer's formula to get them. And we think of this as analogous to Cayley's Hamilton. So we don't have Cayley-Hamilton in the sense that the ratio between the maximum span and the dimension of the vector space is n. We don't have that. We have that as maximum, but there is a combinatorial interpretation in terms of the number of simplices. Now this is useful in graph theory. If you start out with a graph, very typically, in a method introduced by Noga and Abby Virgerson, you can inflate a graph to a hypergraph. And you do it essentially the way I did it here. You start with A and B. You want to know whether A and B are the same graph up to relabeling of the vertices. In other words, is A isomorphic to B? You compute the eigenvalues. No luck. The eigenvalues are the same. So you're in doubt. You don't know whether the graphs are isomorphic or not. What you do is compute A squared. A squared is describing triangles. You now have a 3 uniform hypergraph. To say that graphs are cospectral, you're saying that the coefficients of the characteristic polynomial are the same. It turns out that there is an infinite family of graphs which are cospectral, for which when you inflate them, the coefficients are different. So that inflating graphs to hypergraph using this scheme breaks the cospectral symmetry. Now we don't yet have a complete classification for the graphs which are cospectral that you can break symmetry by inflation. But what is nice is that this scheme can continue. You can inflate a graph to a 3 uniform hypergraph by looking at paths of length 2. You can inflate a graph to a 4 uniform hypergraph by looking at paths of length 4, and so on. Does this hierarchy buy you power in breaking symmetry between graphs? We don't know, but this is a question we're investigating. So in the interest of time, I think this is where I will stop.
Time for questions. Any questions?
Yes?
So, in the case of visual matters, we have associativity law, but maybe here it's replaced with a more complicated relation. Are there any conjectures?
About the So definitely, just for matrices, just as in the case of matrices, there are special matrices which commute. Here, there are special family of hypermatrices which associate, for which associativity holds. And they tend to have to do with symmetries under cyclic permutation of your entries. Now, is there a general relationship which tells you what is the conditions for which you have associativity and you don't? We don't know. For matrices, we know that commutativity has something to do with the eigenvectors. Right. Do we have something analogous here? We don't yet know, but it's a very good question. We don't know yet.
Is it,
Yes.
it's the same question like no characteristic equation either?
Ah, that's a great question. Yes. Should there be something like characteristic equation?
The determinants of Gelfand and Apollo.
Yes. Yes.
Can you?
So we cannot yet express these in terms of Gelfand's determinants, and the reason is very simple. In the case of matrices, the fact that associativity lies, you can always say the determinant for me is the coefficient of the term with smallest degree. You can do something like this here, but the determinant is dependent on the choices you make. For any subset of them that you pick, there's one term of lowest degree, you can pick its coefficient to be the determinant. Now, is there a non-trivial relationship between these guys? We don't yet know. But we have not yet found a way of reducing the coefficients of these into the Gelfand hyperdeterminants. Right.
And will you definitely prove that for small n, they're always independent?
No, so for small n, there exists a generic hypermatrix for which you need n cube.
Yeah, thank you.
Yes, yes, definitely this we show.
That's partially because you have all this non-associativity. The associativity maybe brings that down from n squared to n.
So here, it's more than just associativity bringing things down to n squared to n. Here, essentially, what it's telling you is that these pairs of matrices act as diagonal matrices. And from the spectral theorem, we know this is true. If A is symmetric, we know that all you're doing merely is powering the diagonal, the eigenvalues. And the eigenvalues, if these are polynomial of degree n, you should need just a vector space of dimension n. Now, we don't have an analogous interpretation here. We don't know some canonical variables which you're powering as a result of this. And the hope is that by looking at this combinatorial interpretation, we can say something.
And computationally, it's hard.
Ah, yes. Definitely for doing this symbolically, it's hopeless. Already for 2 by 2 on decent machines, you just can't compute the n cube symbolically. You just stop short. You stop very short of 8. But if you do it numerically, so you have to generate a family of hypermatrices which you think are full rank. And it turns out a very good candidate are so-called orthogonal hypermatrices. These are the ones that behave like orthogonal matrices. If you compute the product, you get the Kronecker delta. And these guys tend to generate a large space. And we know how to generate these canonically by using a variation of Gram-Schmidt.
There's more than one transpose, right?
Yeah. So when we say transpose here, we mean cyclic permutation of the indices. Because a cyclic permutation is going to turn rows into columns and columns into depth. And if you do it 3 times, you come back where you start. This seems like natural because it does exactly what the transpose does on matrices. It cyclically shifts the product. Right. That's a good question. Yes?
Probably I might have missed this, but is there a version where this A to the K is matrix multiplication, right?
Yes, A to the K.
So for entry-wise?
Yeah, so that's the Hadamard power. So if you were doing entry-wise, it's known that for generic, if you're doing this, which is raising powers, then you need the full span. The dimension of this is maximum. You need to go up to n squared plus 1 to get linear dependency. And the reason is you're looking at elementary symmetric polynomials in the entries. And if they're generic, there's absolutely no reason why you don't need all the polynomials.
Is there a name for this or something?
I mean, this is an exercise. I don't think that this is a theorem per se, because it's essentially have to do with roots of polynomials, and you have n squared roots. So if you want linear dependency, you need all of them.
Let's thank Ali again. Thank you.